There, and welcome back to the deep dive. We're cracking open the source material today, giving you the essential insights without all the noise.
And today, we're diving headfirst into the fascinating and sometimes pretty puzzling world of AI thinking.
Yeah, specifically how these really cutting-edge AI models, the ones some folks are calling reasoning models, how they actually process information or try to reason.
And crucially, where their abilities seem to hit some, surprising walls, limitations you might not expect.
Exactly. And our source for this deep dive is a brand new research paper. It's titled The Illusion of Thinking, Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity.
Right, it's hot off the press from Apple Machine Learning Research.
And our mission today is pretty clear. We want to unpack the key findings from this paper, really get into what these large reasoning models, or LRMs as they call them, what they can actually do.
And just as importantly, the unexpected hurdles they face when the problems get tougher.
Yeah, and the paper uses this really clever approach, I thought. Instead of just standard tests, they use these controlled puzzle environments.
Mm-hmm. To really poke and prod at how these models think, or seem to think.
Okay, so let's unpack this. Where should we start?
Well, let's set the stage a bit. You're probably familiar with large language models, LLMs. Everyone's talking about them.
Right, ChatGPT, Claude, Gemini. They're amazing at generating text, summarizing, that kind of thing.
Exactly. They understand and generate language incredibly well. Now, some of the newer, more advanced models are being specifically designed, or maybe fine-tuned, to produce what the researchers call thinking processes.
Thinking processes.
Yeah, or thinking traces. Basically, they output a series of steps, like their reasoning, before they give you the final answer. That's where this term large reasoning models, or LRMs, comes from.
Ah, okay, so they're literally trying to show their work, like in math class, giving you the step-by-step along with the answer.
Precisely. Think of it like an internal scratchpad they use and then share. The paper mentions a few examples like OpenAI's O1 or O3 variants, DeepSeek R1, Claude 3.7, Sonnet Thinking, Gemini Thinking.
Right, those models that explicitly say they have a thinking component. And the idea, I guess, is that showing the work makes them better at complex problems.
That's the hope, yeah. And they do tend to perform better on many standard benchmarks. That's true.
But I sense a but coming.
Well, the paper points out that even with these better scores, their actual capabilities, and maybe more importantly, their fundamental limits, aren't really well understood yet.
Okay.
Are they genuinely reasoning in a flexible way? Or are they just getting, much better at spotting patterns in complex problems they might have seen variations of during training?
That's a crucial distinction, isn't it? Better scores don't automatically mean better, more general reasoning. So what's the issue the paper raises with the current tests, the benchmarks?
They argue that the traditional ways we evaluate these models, often using things like math problems or coding challenges, they have some pretty significant issues if you're trying to measure true reasoning ability.
Like what kind of issues?
Well, two main ones jump out. First, data contamination. It's
Yeah.
a huge potential problem.
Meaning the models might have already seen the test questions or very similar ones in their training data?
Exactly. They're trained on vast amounts of text and code from the internet.
Yeah.
So they might just be retrieving answers or recognizing patterns rather than genuinely figuring things out from scratch based on the rules you give them in the prompt.
Right. So it's hard to know if it's memory or reasoning. What's the second issue?
The second big thing is that these benchmarks usually only care about the final answer. Was it right or wrong?
Okay.
They don't typically give you much insight into the quality or the logical structure of that thinking trace the LRMs produce. Did it follow a sensible path? Did it just get lucky? Was the internal logic sound? Or did it, stumble into the right answer after a lot of nonsense?
You can't tell just from the final results. Okay, so standard benchmarks have blind spots for the process. What did this paper do differently then?
This is where I think their method is really neat. They used controllable puzzle environments.
Controllable puzzles.
Yeah, environments where they can precisely adjust the difficulty. Make a puzzle harder or easier step by step while keeping the underlying logic the same.
Ah, so they can turn a sort of complexity dial very precisely and see exactly where things start to break down.
Exactly. And crucially, these puzzles are set up so you can easily check not just the final outcome, but every single intermediate step the model takes.
Giving them visibility into the actual step-by-step process.
Yes, into the thinking as it unfolds. The paper focused on 4 specific puzzles.
Okay, what were they? Classic logic puzzles.
Pretty much. First, the Tower of Hanoi. moving disks between pegs following specific rules. The complexity scales directly with the number of disks.
Got it. A classic planning task.
Then checker jumping, swapping red and blue checkers on a line. Simple rules, but the number of steps grows. Complexity scales with the number of checkers.
Okay, linear movement, keeping track of state.
Third, river crossing problems. Getting various actors and items across a river with safety rules like, certain things can't be left alone together.
Ah, like the old missionaries and cannibals puzzle, but maybe more generalized.
Exactly, a generalized version. Complexity there scales with the number of pairs you need to move. And finally, blocks world. Rearranging stacks of blocks to match a target configuration.
Right. Another classic AI planning domain. Complexity scales with the number of blocks.
And all these puzzles you see, they absolutely require thinking ahead, following rules step by step, planning.
Yeah, you can't just guess. You need a sequence.
Precisely. And importantly, they require algorithmic reasoning based only on the rules provided right there in the prompt. There's less chance they just memorize the specific solution, especially as you dial up the complexity beyond what's commonly found online.
Okay, so they've got these controlled environments, these specific puzzles. What did they find when they compared the thinking models, the LRMs, to the standard ones without that explicit thinking trace?
This is where one of the core findings comes in. They found three pretty distinct regimes of performance based on the puzzle complexity.
Three regimes. Okay.
And this was comparing LRMs like Claude 3.7 Sonnet with thinking and DeepSeek R1 against their standard LLM counterparts. So
Yeah.
Claude 3.7 Sonnet without thinking and DeepSeek V3 using basically the same amount of computation, the same token budget.
Got it.
Yeah.
Fair comparison. So what are the three regimes?
Okay, regime one, low complexity. Here, the result was actually pretty surprising, counterintuitive even.
How so?
The standard LLMs, the ones without the explicit thinking trace, sometimes performed better.
Better, without showing their work.
Yeah, and they were often more efficient too, using fewer tokens to get the right answer.
Huh. Why would that be? Any ideas?
The paper suggests that for really simple, straightforward problems, the whole process of generating that detailed step-by-step trace might actually be, well, unnecessary overhead. It might even get in the way.
Like overthinking a simple problem?
Kind of, yeah. The standard model can just jump to the answer more directly, using less compute, fewer tokens, those basic units of text, the model processes.
Okay, so the thinking can be inefficient when it's too easy. What about regime two?
Regime 2, medium complexity. Now, this seems to be the sweet spot. This is where that thinking mechanism, that internal scratch pad, really seems to help.
Ah, so the LRMs pull ahead here.
They do. They show a clear advantage over the standard models, and that performance gap gets wider as complexity increases within this medium range. Generating those intermediate steps seems to provide useful scaffolding.
Okay, that makes sense. The scratch pad helps when the problem needs some working out, but isn't overwhelmingly complex.
Exactly. But then there's regime 3, high complexity.
And let me guess, based on the paper's title, The Illusion of Thinking, this is where things get ugly.
You guessed it. In this regime, both types of models, the LRMs and the standard LLMs, experience what the paper terms a complete collapse in performance.
A complete collapse. Not just, like, getting worse, but nothing.
Pretty much. Accuracy drops effectively to 0. Beyond a certain complexity threshold, which is different for each model, mind you, they just can't solve the problems anymore within the test limits.
Wow. Zero success.
Yeah. And this held true for all the reasoning models they tested, the O3 mini variants, DeepSeek R1, Claude 3.7 Sonnet thinking. They all hit a wall.
Okay, that's concerning. But you mentioned something even weirder, the counterintuitive part about their effort.
Ah, yes. This is maybe one of the most striking findings in the whole paper. It's about what happens to their thinking effort, measured by the number of tokens they spend generating that thinking trace as the problems get harder and approach that collapse point.
What happens? Do they try harder? Use more tokens?
No, that's the bizarre thing. They actually start reducing their reasoning effort.
Producing it, even though the problem is getting harder. That makes no sense.
It really doesn't, intuitively. Measured in those thinking tokens, their effort, the length and perhaps complexity of their generated trace, it goes down significantly as they get closer to the point where they fail completely.
But they could use more tokens, right? They have the budget?
Yes, they generally have plenty of token budget left. They could generate a much longer, more detailed thinking process, but they just don't.
Okay.
It suggests a really fundamental limitation in how these models scale their computational effort with difficulty.
So they don't just keep trying harder until they break.
It seems not. It's almost like they sense the problem is too hard and sort of give up internally.
Right.
Or maybe the process just becomes incoherent and they stop generating useful steps much earlier.
Wow. So they don't just fail, they almost fail less trying, using fewer computational steps as it gets really hard.
Yeah, that's really weird. Like a student facing a super hard exam question and just writing down one sentence. That's not a bad analogy, actually. They don't seem to engage with the escalating complexity in a proportional way. So what did they find when they actually looked inside those thinking traces, particularly for Claude 3.7 sonnet thinking, which they analyzed more deeply?
Right. What did the internal thoughts look like at these different complexity levels?
They saw very different patterns. For the simple problems of regime 1, the models often found the correct solution quite early in the trace.
Okay, good start.
But then, bizarrely, they'd often keep going, exploring incorrect paths or alternative solutions after already finding the right one.
That sounds like that overthinking phenomenon people talk about with LLMs, wasting time in compute.
It really does seem like that. They get the answer, but then they just keep rambling, generating unnecessary steps, maybe even confusing themselves later on. Wasted effort.
Okay. What about the medium complexity, where they did better?
In moderate complexity regime 2, the pattern shifted. Here, the correct solutions tended to appear later in the thinking trace. Yeah, only after the model had explored several incorrect paths first. It suggests they might be doing some kind of search or trial and error, maybe even self-correcting along the way.
Okay, so the thinking trace is actually being used productively there to navigate the trickier parts. Makes sense.
It seems so. They're using that scratch pad to explore possibilities. But then, in high complexity regime 3, the collapse zone.
What happened inside the trace, then?
Well, this mirrors the external result. The model simply failed to generate any correct solutions or even long sequences of valid steps within their thinking trace. The internal process itself broke down completely. It never arrived at a valid path.
So the internal monologue, if you will, perfectly matches the external performance. Inefficient on easy stuff, helpful on medium, and just completely lost on the hard problems.
That's a good summary of it, yeah.
Okay, what about some of the other, even more specific puzzling behaviors they noticed? You mentioned some really counterintuitive things.
Right, there were a couple of findings that really raise fundamental questions about what these models are actually doing when they reason. One huge one was their failure to execute given algorithms.
Failure to execute, what does that mean?
It means the researchers literally gave the models they tested, DeepSeek R1 and Claude 3.7 Sonnet, thinking on this, the explicit step-by-step algorithm for solving the Tower of Hanoi puzzle. Like, step 1, do this. Step 2, do that.
Wait, they gave them the instructions? You'd think that would make it easy. Just follow the recipe.
You absolutely would think that. But get this. Providing the explicit algorithm didn't significantly improve the model's performance. And crucially, it didn't really shift that collapse point. They still failed on problems that were too complex, even when told exactly how to solve them.
That is genuinely baffling. If they can't follow simple, explicit, step-by-step instructions for a logical task, what does that say about their ability to perform exact computation?
It really challenges that notion, doesn't it? It suggests the issue isn't just about finding the right plan or algorithm. They seem to struggle with reliably executing a sequence of logical steps, even one handed to them on a silver platter.
Wow. It makes you fundamentally question what following instructions even means for these architectures. Okay, what else was puzzling?
Another really weird thing was the inconsistent failure points across different puzzles. The performance wasn't consistent at all.
How so?
Okay, take Claude 3.7 Sonnet thinking again. On the Tower of Hanoi puzzle, for N10 disks, which is quite complex, needing over 1,000 optimal moves, the model could actually generate around 100 correct moves in sequence before making a mistake.
100 correct moves in a row on a hard problem. That sounds pretty capable, like it has some grasp of maintaining state and following rules over a long sequence.
It does sound impressive in isolation. But now contrast that with the river crossing puzzle. For just N3 pairs, which requires a minimum of only 11 moves to solve optimally.
Okay, much shorter, simpler on the surface.
Right. But the same model failed within the first 5 moves.
Hold on. It can make 100 correct moves on a complex, long puzzle like Hanoi N10, but it can't even manage 5 correct moves on a conceptually different but much, much shorter puzzle like river crossing N3.
Exactly. It's a massive inconsistency. It failed almost immediately on the task requiring far fewer steps.
That's wild. What could explain that?
Well, it strongly suggests that factors beyond just the raw number of steps or the length of the solution are tripping these models up. The structure of the logic seems critical.
Uh-huh.
The paper sort of hints that this could potentially be linked back to data contamination or maybe just data representation. Perhaps river crossing problems, especially beyond ND2 pairs, are just much rarer in online texting code compared to examples or discussions of Tower of Hanoi.
So the model might be less familiar with that specific type of logical structure, even if it looks simpler to us.
That's one plausible explanation. It suggests their reasoning ability might be quite brittle and heavily dependent on the specific type of logical operations required, not just the overall difficulty or length. They might excel at structures they've seen often and fall apart on less common ones.
Okay, this is a lot to take in. Let's try to synthesize this. What's
Yeah.
the big picture here, the main takeaway from the paper's findings?
Well, if you put it all together, what emerges is a more nuanced and frankly somewhat humbling picture of these large reasoning models.
How so?
They aren't universally better than standard LLMs. They can be worse on simple tasks. They have a sweet spot at moderate complexity, yes, but they hit a hard wall and collapse completely at high complexity.
Right.
Near that wall, they paradoxically reduce their effort instead of increasing it. Their internal thinking shows inefficiency, sometimes finding the answer, then overthinking, sometimes needing trial and error, and sometimes failing to find any path at all.
And the execution issues.
And fundamentally, yes, they struggle with things we might assume are basic for reasoning, like precisely executing a given algorithm. Plus, their performance is surprisingly inconsistent across different types of logical problems, possibly hinting at weaknesses related to their training data.
So that title, The Illusion of Thinking, starts to feel pretty appropriate based on all this. It sounds like generating a thinking trace isn't a magic bullet for general reasoning.
It definitely challenges that assumption. These findings suggest there might be some fundamental barriers or limitations in the current architectures or training approaches, especially when problems require truly novel reasoning steps or very strict adherence to logical rules outside of common patterns.
This has been a really fascinating deep dive. We've seen that while these LRMs, these thinking models, show promise, especially in that middle range of difficulty, this source material from Apple Machine Learning Research really highlights some significant limitations. They struggle at low complexity, they collapse at high complexity, and they show these really surprising failures on tasks like just executing instructions or handling different logical structures consistently.
And we should acknowledge, of course, the paper itself notes limitations. These puzzles are just one type of reasoning algorithmic planning, and they had black box access to some models, so they couldn't peek inside the weights to see exactly why certain choices were made internally.
Sure, fair caveats. But
Yeah.
even with those,
The results are pretty stark, I think, and they raise some big questions.
definitely, it leaves us and you listening with a provocative thought to chew on. If these incredibly powerful models struggle with something as seemingly straightforward as executing a simple explicit algorithm they're given,
Yeah.
or if they can handle a 100-step sequence in one puzzle but fail after 5 steps in a much shorter one with a different structure, what does that really tell us about the nature of their thinking?
Is it truly flexible, generalizable reasoning like we humans aspire to? Or is it maybe something else?
Perhaps an incredibly sophisticated form of pattern matching and interpolation, one that's amazing within the bounds of its training data distribution, but breaks down when faced with novel structures or demands for precise, step-by-step logical execution it hasn't effectively learned.
And if it is more like the latter, how far away are we, really, from artificial general intelligence that can truly reason in that robust, adaptable way across all sorts of new problems?
A question definitely worth pondering, especially as we rely on these models more and more.
Indeed.
Absolutely. Well, that's all the time we have for this deep dive. We really hope this gave you a clearer picture of the current state, the strengths, and maybe more importantly, the limitations of AI reasoning based on this fascinating research.
Hopefully shedding some light beyond just the benchmark scores.
Exactly. Join us next time for another deep dive into the source material.